All right, so hopefully everyone can see the hub. If not, someone ask a question. If you can't hear me or see the hub on my screen, then do please let me know. I assume it's working fine otherwise. As you probably know by now, the way you find the materials is to log into your Jupyter Hub, and then on the left side here, you would go to let's see, Tuesday Numpy Yarkoni, and then we'll probably only get through this first notebook. The other one has some extra stuff that you can read later. So if you just fire that one up, that's what we'll be working through. So I'm going to assume that you have a little bit of Python knowledge, if only from yesterday, if you saw my Python tutorial. It won't be the end of the world if you don't have any Python background. You might just have to do a little bit of reading after the fact. And so what I want to start by doing here is motivate this thing called Numpy and kind of explain why it is that we don't just do all of our data analysis in neuroimaging, most other scientific fields, in sort of like Python, base Python out of the box. And the core idea here is to start by just thinking about like what kind of data we work with. When you think of something like, I'll take fMRI, but most neuroimaging data has the same sort of flavor, which is to say data sets tend to be large and they have multiple dimensions, right? So in many disciplines, we kind of think of data as just like a spreadsheet. Like we do a lot of behavioral analysis in psychology or social science. Often your data is just a spreadsheet. Like rows for, let's say, subjects, and then columns. And that's not a huge amount of data. It can be, but often it's manageable. And so you might actually be able to do your analysis in almost any language fairly easily. But once you start talking about things like fMRI data sets, let's take a resting state data set, which might have 20 participants. If each one scanned for 30 minutes and the TR is 1 second, that's like 1,800 scans per person. And then you have obviously the spatial dimensions. So they might be something like, roughly 100 by 100 by 100 observations. And so that's already 36 billion observations. Oh, I'm sorry, I should have mentioned, if refreshing one, so if the folder is not showing up for you, I tend to do things last minute, I apologize. What you'll have to do, actually, now is a good time to do this, is you'll have to actually go to File, Hub Control Panel, and then you'll actually have to shut down and restart your server. There might be some other way to update it, but this one works for sure. So just stop my server, and then I hit start my server, and then so I apologize for that. It's not there, and this will be true throughout the week. I mean, there might be materials you're not seeing, so you'll have to restart your server. If someone does know of a faster way to do that, you can also pull from Git, but that only works if you sort of are familiar with Git at this point. So if not, just it'll take you 2 minutes, but do restart the hub. And same thing goes throughout the week if we run into the same situation. So yeah, thanks a lot for bringing that up. That's important. Okay, so where were we? Oh, oops, accidentally. There we go. Okay, so we have this data set, right? And we might have like 30 billion observations just for a fairly typical, not even particularly large resting state fMRI data set. And the data has a certain structure. So one way to represent it, let's say that you take a single subject, right? It's not like you just have like a very long 36 billion long series of numbers. There's a structure there that we want to respect. And so if you think of taking like one subject's data, a very natural way to represent it, this is an image I borrowed from NILearn, which is a neuroimaging library that Elizabeth Dupre is going to talk about later this week. This might be a very natural way to represent it. So if you look at each sort of cube here, it represents one moment in time, one volume. And so T is like let's say the current moment in time, and there's a three-dimensional brain there. Okay? So there's a natural structure to the brain that we want to respect. And then we can stack another volume next to it and go back in time. And so one thing that kind of suggests right away is that if we want to access certain chunks of that data, we should be able to do that without having to scan the whole four-dimensional array, right? That would be kind of unfortunate if we needed to like scan every single voxel just to get like, let's say we want just like the information at one point in the amygdala for every scan. But if we have to do this naively, like if we were to do this in Python, we would probably have to store this data in lists. out of the box, Python doesn't really have in standard library structures that are sort of efficient in representing arrays. And so we might store this as a list of lists, right? So maybe the outer dimension is time, and then inside that is like the x dimension, and inside that is y, and so on. So if you imagine then having to look through that list of lists for just one point in the amygdala, it might look like this. This is pseudocode. You can't run this. I'm cheating here, just as a little aside. You can see that this is actually marked down. I didn't want to like actually load a 4-dimensional image just to make this point, but something like this, right? Something like the pseudocode would be required. You basically loop over the time dimension and then loop over like the x-axis and then the y and the z. And you'd have to do that for every single point, like in this case, like billions and billions of data points, just so you could determine at each point whether that voxel is in the amygdala or not. That would be extremely inefficient. Every time you need a data point, you have to like search the whole space. That would be very bad. And that's a very, very naive algorithm. Have a little bit of it here about big O notation. So computer scientists have a way of representing what's called the time complexity of the algorithm. You basically have to do like n to the 4 operations because you have sort of these nested loops. So as the size of that array grows, as you have more data, the number of operations you have to do, if you have to look at every single data point, grows in polynomial time. It goes very fast, and that's bad. However, if you know something about Python, you kind of might be thinking, well, we don't really need to do this like nested looping thing because we know about list indexing. So even if we have a list of lists, as long as we know where that particular voxel we want is, like maybe we know that it's these are the indices. So it's for every volume, it's at position 20, 18, 32. Then we only need one loop. We just need to loop over the time dimension, and then we can pull out the exact element we want. And that's a big improvement. Now that algorithm runs in linear time, it's really just the number of time points now that matters. And that's great. So you might think, okay, we could still do this in Python, and it's not that bad. However, there are still a couple of limitations with using Python lists as your sort of core data structure. One is that for those of you who watched the Python talk yesterday or know this from other places, Python is a dynamic language. And so when you write loops of any kind, every time you access a variable, the Python interpreter has this extra overhead, has to figure out like, what is this variable? Is this a variable I can apply the particular operation to? And that over time, in the aggregate, that can add up really quickly. And so even though lists themselves may be pretty fast, the fact that you have to access variables or elements in there individually in Python can slow things down quite a bit. And the other problem is that Python is not really designed for numerical analysis. And so there's just not a lot of tools in the standard library to do things like math on arrays, matrix operations, transform arrays in various ways. You can do that if you want, but you're going to have to write a bunch of Python code to do things that in an environment designed for numerical analysis should really be like one line, should be one function call. And so to solve those problems, Numpy was developed. So Numpy is really the backbone of the numerical and scientific computing stack in Python. Most of the libraries we'll talk about, many of them at least, Pandas, scikit-learn, nylearn, ultimately are built on Numpy. And sometimes there's several layers. So like, for example, nylearn is built on scikit-learn, which is built on Numpy. But under the hood, for most of these things, we're using Numpy arrays because the fundamental data types that Numpy provides are extremely efficient and they're very useful. So we'll spend almost all the time today talking about Numpy. I'll leave a little bit of time at the end to just sort of introduce Pandas, but just unfortunately in the interest of time, we were probably a bit ambitious in the description of this presentation. I think doing Numpy and Pandas in like an hour and a half is probably not reasonable. But the good news is there's lots of resources out there for learning both of these things that I'll point you to later. One in particular is particularly good. Okay, so let's start by importing Numpy. So as you probably already know in Python, outside of a very, very small set of built-in functions, if you want some functionality, you're going to have to import it. And so here I'm assuming you have Numpy installed, which is true on the Jupyter Hub. If you run this locally, you probably need to install Numpy ahead of time. But assuming that's done, if you import Numpy, then you should have it available. So you're on that cell, now you have Numpy available as NP. And this is conventional, right? You can call it whatever you want, or you can just say import Numpy. But the convention, to save you a little bit of typing, is to use the short abbreviation NP, and do try to stick with that convention because everyone else uses it. So when you see NP in someone's code, you know that they're calling NumPy. So what does NumPy give us? The core data structure in NumPy, really the kind of the fundamental, the most important aspect of this is what's called the n-dimensional array. But I'll just talk about them as arrays. And generally, you hear people say NumPy arrays, they're talking about this ND array data type in NumPy. And so as the name suggests, an ND array, an n-dimensional array is an array with an arbitrary number of dimensions. So, so you can have, like 8-dimensional or 15-dimensional arrays, although in practice we'll typically be working, at least in imaging, with something on the order of like 3 or 4 dimensions. Unlike Python lists, NumPy arrays are homogeneously typed, which is to say, every element in the array has to have the same data type. You can have an array of floats, you can have an array of integers or strings, but you cannot have an array that mixes floats and integers or strings, etc. There is something called a structured array NumPy provides. I'm not going to talk about it here. It's pretty uncommon to actually have to use that, particularly since Pandas came along. But it does exist. If you really need to represent some mixed data types in a format that NumPy can work with, then you can look into structured arrays. But for the most part, you think of arrays as homogeneously typed. And that's one of the reasons why NumPy is much faster than Python, is because we know the type ahead of time, so we don't need to actually examine every single, or the interpreter doesn't need to examine the type of variable it's working with every single time it accesses null. It knows that this entire array is guaranteed to have this particular type. Okay, so how do we create arrays? As with any other object in Python, we actually initialize an object before we can do anything with it. And there's lots of different ways to initialize arrays in NumPy. We'll just look at a couple here. So probably the most common is initializing from an existing list or some kind of Python variable that NumPy can handle and knows what to do with. And so here's an example where we're constructing a new array. So the array initializer here, you can think of that as a so the array is the class. You can think of it as essentially as a function that takes some input and figures out whether it can construct an array from that. So in this case, we're passing in a list, right? So this would be equivalent, just to make it absolutely clear. This is no different than saying like my list equals that. We could declare this in advance, and this is the same thing. And nothing, you don't see anything fancy here. It's just that when you initialize an array from a list, NumPy will construct an array, and that's the printed representation of the array. It looks very much like the list. It just tells you, oh yes, this is an array now. It's not a list any longer. Right? If I were to print my list, all you see is just the contents. Okay, so that's probably the most common way of initializing an array, or well, a common way is when you have some data already in a Python data type, and you just pass it in, and NumPy figures out what to do with that. And it's pretty good about figuring out what to do with kind of a fairly wide range of values you pass in. So, for example, if you want a 2-dimensional array in Python, naively you might represent that as a list of lists, right? So the inner list has a bunch of elements. And so if you have this list here, like in Python, and you pass that to NumPy, it will understand that, okay, you probably want me to represent this as a 2x3 array. So that there's the outer list is the first dimension. There's 2 elements in that, and then inside each of the inner dimensions, there are 3 elements. And so what you end up with here is a 2x3 array. And the same principle extends. If you passed in a list of lists, then NumPy would construct a 3-dimensional array. One thing to be careful though is this only works if the inner lists have the same number of dimensions, right? So if I try to do this, I feed it a list, and one of those lists has 3 elements and the other has 2, it doesn't like that, right? Actually, interesting. Oh, sorry, it's not that it will do something, right? But notice what it does is it interprets this as an array of lists. So now this array actually only has 2 elements. It's 1-dimensional, has 2 elements, but the elements are lists. So remember, Python or NumPy arrays are homogeneously typed, but they can be of various types. You can have an array of lists, which is represented as this object data type. but this is probably not what you want, right? And so you want to be careful when you pass inputs that you're passing in the right thing, because NumPy will try to figure out what you mean, and if you make a mistake, it'll try to respect what it thinks is your wishes. And so you can play with that. You can also try passing in strings and mixed data types and see what happens when you try to construct a NumPy array. Okay. Alternatively, though, you might want to start with a brand new array. There's no previous data that you're basing your array on. You just want to construct something from scratch. And so there are many ways to do that. One very common one is to use the zeros function, which constructs an array and fills it with zeros. And so here I'm constructing a two-dimensional array, and the tuple I'm passing as the argument is the dimension. So this is saying, this is a typo, this should say 5 by 10. I'm saying construct a new array 5 by 10 and fill it with zeros. There's also a ones function that does the same thing for ones. And we'll talk about, actually in a moment, we'll talk about full, which is the same for other values. So you can see that the only difference between constructing a three-dimensional array and two is you have an extra dimension in the shape tuple you're passing, and the number of, and the values of, it tells you the size of each of these dimensions. So this is a 2 by 4 by 8 three-dimensional array. Okay, there's a whole bunch of other initializers that give you various kind of types of arrays. I shouldn't say types. They give you arrays with certain properties. Here's one. This is A range is the equivalent of Python's range. It's only called A range to distinguish it so they don't get name conflicts. And so what that does is return an evenly spaced set of values within a certain range. So starting at 4 and going up to 10, it can also take a step argument. So you could also say, give me every second value between 4 and 10. So that's another way to construct an array. You can sample random numbers. So there's a random module inside NumPy. It's extremely useful and has various random number generators. This one is sampling from a normal distribution, and the arguments are the parameters of that distribution. So here I'm saying, please give me an array with values sampled from a distribution, normal distribution with mean of 2, standard deviation of 4, and the size of the array or the shape should be 10 by 2. And so that's what you see. And because this is random number generation, if you rerun the cell, you're going to get a different set of values every time. And there's lots of other random number generation functions you can explore in there. So, for example, you could have random integers if you want. So here I'm saying, give me a 10 by 10 array of integers under 10, or between 0 and 10. And you can see all the various functions, classes, etc., all the functionality you have inside that random module. So there's a lot, and this is true in Python. Or NumPy is a huge library. There's all kinds of cool stuff inside there. So I'm really just showing you some very small slices of what's available. Okay, NumPy full I mentioned already. It's just like zeros or ones, but it gives you an array with full of a particular value. So here I'm constructing a 5 by 5 array with all values set to 400. And there's a variety of other initializers you might use depending on what you're doing. All right, so that's, let's see if there's a question. What would the use of an array of all the same values be? There's many answers to that question. Let me focus on like zeros and ones, which are like by far the most common situation. Very often you'll want to initialize an array that's going to store values of some operation, right? So you might think of zero as empty, like you just initialize all zeros. That way you know that if you don't fill a particular value, then there's no value there, right? Zero is a reasonable default for many things. Ones, you might, for example, think of like an intercept column. It's very common to add to some design matrix a column of ones, and so that will give you that. Beyond that, there's lots of, I can't think off the top of my head like that, like a big class of situations, but there certainly are lots of situations where you will want to construct an array that has like a constant value. If you're doing linear algebra, that's quite common because you might want to construct like an array that you're going to multiply by another one that has to have maybe like all the same value and so on. So there are uses for that. That's a good question. Okay. All right. So we have ways of constructing arrays. Once we have arrays, what do we do with them? Well, first we might want to know what's actually in them. What's the type of value they store? How big are they? And so two really useful methods for just inspecting arrays and figuring out what we're working with are shape and d type. So shape just shows you the shape, and it's basically what you, some of these initializers already passed in, right? So it's an attribute on the array. So, oops. Oh, this is what I did here. Interesting. Okay, let me. There. I don't remember if I was screwing around earlier, or if that's actually what I saved to the hub, but in any case. So I'm just initializing a list here from, or an array from this two-dimensional, or this list of lists. And if I ask what is the shape of that, once it's constructed, it's 2 by 3. Right? So it has 2 elements along the first axis and 3 along the second axis. If it's two-dimensional, we can also talk about rows and columns, but this is a generic structure. So in 8 dimensions, you probably wouldn't want to refer to the first column or the first dimension as rows. But I might slip into using that language because most of our examples will be two-dimensional. Okay, so we have the 2 by 3 array. And we can tell by looking at that it has 2 dimensions, right? There's 2 elements in this shape tuple, but that's probably not the best way to actually have to figure out how many dimensions there are. And you can access the number of dimensions directly via the ndim attribute. So that just tells you how many dimensions the array has. And there's various other kind of attributes of an array you can inspect. The other really important one, though, is d type, which tells you the data type of the values in that array. So earlier, we initialized an array called myr in R3D. Let me just kind of remind you what those look like. So here's the first one of these, right? And here's the second. Okay. And so now we're just asking what data type these 2 arrays have. And so the first one is d type of int64, so 64-bit integer, and the second one is data type of 64-bit float. And why are they different? Because when you initialize an array from a list, NumPy tries to intelligently figure out what data type to use, and it will generally use the sort of the simplest data type it can. If it can get away with integers, if everything looks like an integer in the list, then it will make the data type integer. If there was a single float in there, though, it would basically make the type at that point float. But when you construct, so this R3D we constructed with NP zeros, and by default that will give you a data type of float 64. However, if you want to explicitly initialize an array of zeros that are integers, then you can just force that by saying d type equals x. So you can specify the type of actually many NumPy functions, almost anything involving construction of a new array, for instance, will let you specify the d type. So you can explicitly exercise control over the data type of your array. The question is, I missed the array shape fix. It wasn't really, well, it doesn't really matter. You could take any, that was just for the sake of this example, you could take any array and just apply dot shape to it. So it doesn't have to be that particular one. That was just because I wasn't sure I'd have the array. I thought I did. Okay. All right, so, and NumPy, I should mention, has a whole bunch of data types. So beyond just integers and floats, NumPy does allow you to represent complex numbers. You'll notice these are int64 because they're using 64 bits to represent each value, which is good because spaces or memory is not really at a premium these days for the most part, and we kind of want precise computation. But if you value memory over precision, you could use int32 or float 32. And beyond it, there's also a variety of data types that are sort of even operating system specific. So there's something like 30 data types if you look at all the various ways you can construct them. But for the most part, really, unless you're sort of running into memory issues, which you are, there's probably better solutions than this. You probably will you can think of these as instant floats for the most part, integers and floating point numbers. And that will cover the vast majority of use cases. Okay, so we have arrays, we can build them, and we can inspect them. Now we can start doing things with them. One of the most common things we do with an array is we access data. We either take data out of the array or we set values on the array. And that, just like in Python, is called indexing, just like with lists in Python. So how do we index NumPy arrays? So let's start with one dimension. And it looks almost exactly like it does in Python with lists. So if you get list indexing, you already know how to index one-dimensional NumPy arrays. So here we'll construct our array, just so you can see it, right? That's the array. And just like with Python lists, to access the ith element in the array, we just pass that index inside the square bracket. So this is saying, give us the fourth element. Right? Remember, Python is indexed from 0. So this is the fourth element. And just to make sure, 1, 2, 3, 4, sure enough. So that's giving us back the fourth value in that array. Just like with lists, you can index from the end of the array. So if I say -2 here, that's saying give me the second to last value, which again you can verify is in fact the correct one. And again, just like with lists in Python, you can use slices. So we can say give me a sequence of values using the colon operator. And so if I say if I say 2 to 6, I'm basically asking to be given back the values stored starting at position 2 and up to, but not including 6. And so I get back these 4 values. You can also omit one of these numbers, which would then be interpreted as everything. So either everything up to this point or everything from this point. So here I'm saying, give me all the values up to the position 4. And I could also done opposite. I could say, give me all the values starting at position 4. It's a question. Does indexing from the end of the array start from index 1 rather than 0? Yes, that's correct. So yeah, I suspect it's mainly because I'm not sure, but I suspect it's because like -0 would be a rather odd construct, right? Actually, that's got to be the answer. Like -0 is the same thing as 0, and so you can't actually start. So indexing from the end starts from 1. Yeah. Okay, so we can slice up to the 4th position if we want. We can also use the step argument here. So this is saying start at position 1, proceed until the second to last element, but only take every 3rd element along the way, step of 3. And so that's what you get there. So you can experiment with this and sort of play around. And there's some other tricks you can do, like you can reverse. If you pass a negative step value, then it will actually reverse. It will proceed from the end to the beginning. So there's other kind of clever things you can do. So that's one-dimensional indexing, and everything I said, I believe, applies to Python lists as well. So there's no surprise there if you're used to working with lists. But of course, the power of NumPy arrays is that they have multiple dimensions. Otherwise, we could live with a list. And so we're going to explore some things you can do indexing with n-dimensional arrays. Now, instead of using sort of toy examples, I figured since this is a neuroimaging course, it would be nice to actually use neuroimaging data. But we're going to cheat a little bit. So I'm not going to really explain the process of getting the neuroimaging data into an array, because Chris Markevich is going to dedicate a whole, I think, 2 hours on either tomorrow or Thursday, I think Thursday, to this. And so he'll talk about a package called ndarrays that he maintains along with many other people, and really explore how the data represent, how you get them in. For our purposes, just all you need to know is what I'm doing here is just taking a nifty image on disk and reading it into a NumPy array. And that's all we'll say about that here. But you can see there's not much to it. We're just loading the image, essentially. Now we have that volume, this anatomical data loaded into our data variable. Let's look at its shape. 91, 109, 91. Those of you who have done fMRI analysis before that may have a feeling of familiarity to you, right? This is these are the dimensions of the MNI 152 2mm template, and that's exactly what this image is. So this is just like the canonical. There's nothing special about it, but it is the most widely used historically space in which fMRI analysis was done at the group level. And we can also look at the data type. It's a float 64. So we have an array, a 3-dimensional array of floats that we know contains anatomical information. And now we can start working with our image. And so let's look at how indexing works in multiple dimensions. So remember, in Python, if you want to do something like this, you'd have to have a list of lists. And so if we had a list containing this data, we would probably have to index it doing something like this. Essentially, we're saying, take the 4th element within that list, and then you get that value back. And then you can look within that, and so on. And so you would have this sort of stacking of these like square brackets. But Fortunately, we don't have to do that. There's less typing involved in Numpy. In Numpy, you can pass all the indexes within the square brackets. And so this is the way you index in multiple dimensions. So this is saying take that three-dimensional array and basically get the data you find at position 45 along the first axis, and then 54 along the second, and then 45 along the third. And so this gives us back some value, and the value here doesn't really mean anything. I mean, there's no absolute meaning here. There's just the intensity of the image, and this is an image derived from multiple scans, and so you don't really care about the absolute value, but certainly the relative variation across that volume is going to be informative, because we can map those values onto brightness values or different colors, and we'll do that in a moment. We'll see how easy it is to visualize an image, a brain image stored in this kind of volumetric representation. What about multiple values? So great, we know how to pull out an individual value, but can we do slicing in multiple dimensions? The answer is yes, and the syntax is very similar to what we saw earlier. This is it's saying, please take a slice along that first dimension, give us the first 20 values, but still pulling only from the 54th position, or I should say like the position 54 along the second axis and 45 along the third. And so what this is going to give us is an array now, not a single value, right? Because we're slicing, and so there's multiple values coming back. It's giving us an array of 20 values, and it's a one-dimensional array because we're not slicing in other dimensions. If we really wanted to, if we wanted to get a two-dimensional array back, you could pass this as the index. Notice that this, in some sense, means the same thing, right? Because remember, the end number here is exclusive. So this is basically saying start at 54 and go up until 54. That's the same thing as 54, but because you're specifying this as a slice, NumPy interprets that as, okay, you want to retain the second dimension. And so that would look different because now this is actually a two-dimensional array. Just to make it really clear, here's the shape here, right? It's two-dimensional, has the same 20 values, but it's represented as a two-dimensional array. Whereas if we do this, we actually just get back a vector, a one-dimensional array with 20 values. Okay. Oh, this is what I just said. Okay. Now, great. Does that principle extend beyond slicing along one dimension? Yes, it does. If we want to take a two-dimensional slice through that, so we have a cube, and we want to pull out just a plane in that image along, let's say, the third axis, the syntax is exactly the same. Notice here we're just passing these colons without any numbers around them, and that you just interpret as all. So if there's nothing like this or like this, then that colon just means take everything you have access to. And so this will give us all values along the first dimension, all values along the second dimension, but only for index 45 along the third dimension. So you can think of this as basically if you have a cube, right? We're just like seeking to a particular position along the third dimension and taking a slice. We're taking all the values through that slice. So maybe if I just pop up here, right? Like if you think of this first value, maybe we're just like taking a slice through this axis at this point, and so we're just like cutting through along the sagittal plane, for example. And so let's go ahead and do that now. And so now you can see a two-dimensional result. And the reason there's lots of zeros here is because in the space, the brain only occupies about a quarter of the actual volume, because it's obviously it's like sitting inside this cube. And so the zeros, basically zero just means there's no value, there's no anatomical information here. So all of the edges are basically zero, and at some point, if you keep going in, you'll hit values, non-zero values, where there's actual brain information. We can verify that this does indeed give us a two-dimensional array, and it does. Okay, so I mentioned that we're actually working with real imaging data, and one thing that's nice about that is we actually can make sense of it. We're not dealing with like a bunch of random numbers that we look at but have no real intuitions about. This is an actual anatomical image. And so I'm going to cheat a little bit again and look ahead to Kirsty Whitaker's lecture. She'll talk about visualization and matplotlib at great length. I'm not going to explain what I'm doing, except to say there's this library called matplotlib that, just like the Numpy everything is built on top of that. Matplotlib is the foundation of many, many, many visualization libraries in Python. But here we'll just use Matplotlib itself. So I'm just calling this IM show or image show function, which you could just hand a two-dimensional array and it will very nicely plot there with some default color map you may not like, Redis, but that's fine. Right? You can change the colors and you'll see how to do that, I think, in Christy's lecture. But that's kind of cool, right? So like we kind of take this for granted, but it's worth taking a moment to stop and think about like how neat it is that in like 2020, building on like 70 years of like computing and engineering, we can now in like 2 lines of code basically represent like a composite of a bunch of people's brains on our screen. There was required using a machine that took pictures of people's brain without cutting it open, right? And like it's kind of incredible. Easy to take for granted, but it's really pretty kind of amazing. It's not specific to Numpy or Python in any way. You can do this in every other environment, but the fundamental idea that we can do this is, I think, kind of incredible. Can you output the dimensions where values are not 0? Yes, we will, I believe. Actually, I don't know if we'll talk about it. That'd be a little more. If there's time, I'll do that. But you can look at the second notebook will get you most of the way there. So I talk about Boolean indexing there, and so that might help. But if you mean like the question is like, can you like basically shrink the bounding box essentially down to the point where it only just touches the brain? Yes, you can, but you'd have to write a little bit of code to do that. There might be a function somewhere in NumPy. There's so much in there that it would not shock me if there's actually a one-line function that does exactly that. But off the top of my head, I don't know of it. Right. So in 1 line of code, we get this nice slice. All right. Now, one thing to notice about this, if you work with brain images, you might actually recognize this. You probably look at this and be like, oh yes, right. That's the sort of like right through the middle of the brain. It's basically the slice that corresponds to z equals 0. So if you know about how brains are represented in standard coordinate space, right? So the x-axis would be sort of moving from left to right along the brain, y is front to back, and z is up or down. And so that's what this is. This is essentially the slice you get at z equals 0. And you might note, right, that it's not indexed with 0 here, it's 45. Why is that? Well, that's because image space and world space are different, right? So what kind of the way you map the coordinates that you give the human brain can be whatever you like, but a NumPy array has to start, remember, index starts at 0, right? So every NumPy array's indexes are going to run from 0 to whatever. And so there is some mapping from these things, but that's again something that I believe Chris Markevich will talk about a lot when he talks about NIBabble, or just I hope he'll talk about the affine array that contains the information that maps the between these things. It tells you how this image corresponds to points out in the real world in whatever frame of reference you're used to thinking about images in. The important point, though, is like just the fact, knowing that there's a mapping, and knowing that when you take a slice along this third dimension, you're slicing along the z-plane, might lead you to think, okay, good. Well, that means that each of the other dimensions are mapped one-to-one to dimensions of my array, and so I should be able to plot other slices, like coronal slices or sagittal slices, and that is right. So here we're slicing at a particular point along the coronal axis, and so you have a coronal slice. Notice that it is not oriented properly, or at least it's not the way you would normally look at coronal slices, right? It's sort of the brain on its side, and I'll show you how to fix that later. There's a question. Some of the IAM show calls are terminated with colon. That's not the only reason for that. Actually, I'll show you what happens if you don't have that. That just suppresses output. It's not special to it's actually you can add a colon to every line, and it will just suppress the output. So if you don't do that, what happens is you get some information about, basically, because there's both a plot and you still get the results back, you get this like information here about the variable, the plot itself, and then the thing. And so I'm just suppressing that just so you don't have to look at that. There's nothing that functionally doesn't mean anything. That's a good question. Can you use logical indexing in which you're indexing an anatomical mass? Yes. Again, I may or may not talk about that if I have time, but there is an example of exactly that in the notebook number 2 there. Yeah, that's a good question. All right. So yeah, so we'll come back to this orientation issue. And the reason for this is because, again, like the image space doesn't have to be the same as world space. There's no particular reason why the particular orientation you're used to looking at a array and when you look at images, right, has to be the way it's stored inside that array. And so in this case, it's not. So there's some transformation that would orient this image in a way that you are happy with. And we'll come back to that in a bit. But that should give you a general idea of indexing in arbitrary n dimensions. What about setting values? So we've access values, can we also set values? And the answer is yes, and it's exactly the same syntax, just with an assignment. So here's an array, one-dimensional array, and if we want to set a new value at position 2, index 2, we just say, you know, array at 2 equals 100, and so now that value has been changed to 100. What about multiple values? As you might expect, slicing syntax still works beautifully. Here I'm saying find that subarray that starts at position 2 and runs until, but not including 4, and replace it with the following values. Notice you can pass a list. So Numpy is clever, and this saves you some typing. I don't have to be explicit and say, here's an array. And this is another benefit of dynamic typing in Python, is that, you know, like, well, actually, I think that's not strictly correct. But the implementation of Numpy lets you do that. So you can pass in a list, and it will figure out that, sure, this can be turned into an array and plugged in there. One thing to notice here is and I'll come back to this, the dimensions of this shape has to match. So you can't, like, this refers to a subarray with 2 elements. If I tried to do this, I would get an error, right? You cannot replace a 2-element sequence with a 3-element sequence, right? Numpy does not automatically grow or magically the array, and you wouldn't want that. And so you have to be sure to pass dimensions or shapes of replacements that it's expecting. Although, and we may talk about this later, you can always pass a single value. That will always work because that's just interpreted as create an array of the same size as the target and just fill it with that one value. This is called broadcasting, which I also talk about a little in the second notebook, which we may or may not get to, depending on how we do on time. Okay, and the same idea goes for arrays with more than one dimension. So, so here I'm creating a 2-dimensional array, 5 by 5, it's all zeros. Then I create a 3 by 3 array of ones. And now I'm going to replace a chunk of that 2-dimensional 5 by 5 array, it's got to be a 3 by 3 subarray, with the ones. And so here's what that looks like. And so initially it was all zeros, but this line here says, basically identifies this subarray within that bigger array and then replaces it with the values we just created, the ones. So that's indexing. We can access values, we can set them. There's some subtleties to that I also cover in the second notebook. There's a difference between what's called copies and views. But if you're new to arrays, I would suggest not worrying about that right now. More than likely, at some point, this will bite you in the ass, and you'll learn the hard way that there's a difference between a copy and a view. But you can read more about that. Do you also have I? Yes, we do, and I actually think I have an example of that a little farther down. But there is np.I will give you an identity matrix. And there's lots of other linear algebra functions that I'm not going to talk about, but I will touch on the linalg module, and you can go and look at everything that's in there. But just to make the point, you could do this. So this will give me a 5 by 5 identity matrix. Yeah, good question. So now we have arrays, we can access values, we can set values. Let's start doing things with them. And one of the first things we might want to do is restructure, reshape them. So very often you start with some, it's very common to have just like a vector of values, and you want to reshape it into multiple dimensions. So for example, here I have a 1D array with 100 elements, 0 through 99, and maybe I want to turn that into a 10 by 10 array. And so I can use the Numpy reshape function, and I just pass the first argument as the array I want to reshape, and then the second is the shape that I want the output to be in. So here I can say 10 by 10, and there you go. And you can see how it's filling it in, right? It starts along so it basically constructs that 10 by 10 array, And then it starts along the first element of the first axis and populates that. Once it gets to the end, it goes on to the second element of the first dimension and keeps going. And so it'll fill it up that way. You might expect that there to be some constraints on the shape, right? So like I cannot say, you know what, take that 100 element array and give me back a 10 by 17 array, because it's not at all obvious how you would take 100 elements and return something with 170 elements, right? You wouldn't want Numpy to do like some crazy internal, make some crazy internal assumptions about, oh, maybe you want the first 100 and then the 70 after that, or just like the first 70 or something. That would be a little weird. So the shape does have to match. There is some subtlety to that. I mentioned broadcasting already. It doesn't have to exactly match. And if you leave one of the arguments open, so if I don't, you know, even though I want a two-dimensional array, I don't know, let's say I don't know how long the input is, so I don't actually know how many elements there will be in the output. I just know that I want 10 rows. So I can wait, is that right? Oops. Maybe it's not. I'm blanking on the syntax for, does anyone know off the top of their head? Okay, I'll look this up later. There is a way to just, maybe it's 0. There's a way to indicate that you want Numpy to figure out, provided there's only one empty dimension, what the actual, like how many elements along that axis to provide. But that's a subtlety. Okay, so, and of course you can reshape, oh, that's right, it is -1, I think that's right, yeah, perfect, thank you for that. Right, so if you say -1, then Numpy will interpret that as basically like figure out what like the free parameter there is. And so if you have only one missing value, then it can always determine how many elements along that remaining axis. So if I did this, right, then how many, you know, what is the other dimension? It has to be 5 because we know there's 100 elements, and the first dimension is specified to be 20. So the second dimension has to have 5 elements. Okay, so that's reshaping. Transposition is another really common restructuring operation, and there's a transpose function and so transposition reverses the order of an array's axes. So if you start out with something like this, right? Initially, I initialize a 5 by 2 array. If I transpose it, I'm basically flipping the axis, and so I get a 2 by 5 array. And for convenience, Numpy provides this .t attribute, which is exactly the same. And so if I create an array and I say x.t, that's the equivalent of saying np.transpose of x. So those are just to say the typing, essentially. Although transpose is more flexible, it has additional, it has an axes argument, so you can actually indicate which axes you want to transpose, which is not true here. And so now that we have that trick up our sleeve, if you remember the coronal brain slice we had earlier that was sort of not oriented properly, now we can actually fix that. And so I'm taking this coronal slice, the same slice we had before, and notice I do 2 things here. There's kind of 2 operations going on. One is I'm transposing it, and I'm transposing that 2-dimensional data. And I'm also doing this little slicing trick here. Remember, I mentioned that this is reversing the order. So I'm not going to spend more time on this, but I encourage you to play around with this a little bit and figure out what's going on. You can just like muck around with this. And I also have a little exercise that you can try, which is to come up with a correctly oriented image, but where the slicing happens before or the indexing happens before the transposition. So you can play with that. How you get the drop down more info? Good question. So this is a Jupyter thing. Anytime you're inside a function, you can hit Shift Tab, and that will show you the signature of that function. And if you have an object, if you type the dot and then hit Tab, in theory, I'm not sure why this is. Maybe it's just slow. I did execute this. Yeah, I'm not sure. It's a little weird. I'm not sure why it's not. Try it with a different variable. Yeah, okay. Maybe it's an online thing or some weird interaction. But if you have an object in principle, at least, if you just hit tab after that, it should show you all the available completions. Why that's not working for the array here, I'm not entirely sure. So that's just a little Jupyter trick. Is the T attribute built into Python? Yes, it's not built into Python. It's an attribute of arrays. Remember, we are working with objects of type array here, and in the definition of that type is a attribute T, and I'm guessing, I have a strong suspicion that if you go and look at the implementation in the Numpy code base, it's just essentially an alias. It's just a wrapper around NP transpose, right? So my guess is it's just purely for convenience, but it's defined inside the Numpy n-dimensional array class. And someone's suggesting that it's just slow to complete, and that could be. There are a lot of attributes there. Okay. All right. I guess 9:52 on the West Coast. Let's take. You know what? Actually, let's just finish stacking and splitting. That'll be a nice breaking point. So, and then we'll take a break. So we can reshape arrays. We can also combine multiple arrays into one, or split one into multiple ones. So here we're creating two separate two-dimensional arrays, both 10 by 2, and we might want to bring them together and join them or concatenate them, or stack them. And so Numpy has a concatenate function that will allow us to do this. We pass in a list of the arrays we want to concatenate, and we specify the axis along which we want to concatenate them. So if you think about, we start out with two 10 by 2 arrays, and we want to concatenate along the first axis, which of length 10 in each one. So that's going to take like these long arrays and just like concatenate them along this axis vertically, essentially. And so the result is a 20 by 2 array. We could have said axis equals 1, and as you might expect, that would do it along the other axis. So that stacks them horizontally. That takes that 10 by 2 array and stacks next to it another 10 by 2 array. And this doesn't have to, they don't have to have exactly the same dimensions. They only have to have the same length along the axis you want to concatenate. So I can have like a 10 by 8 array, and as long as I'm concatenating, as long as they match along on the array I'm concatenating along, this will work fine. So here we get a 10 by 10 result. Right, so hopefully that makes sense. Now, for convenience, Numpy does give you vstack and hstack functions, and they're just aliases to concatenate where the axis is already fixed. So vstack is vertical stacking. It's equivalent to concatenate where the axis equals 0, and hstack is equivalent to concatenate with axis equals 1. Right? So those are just pure syntactic survey. They just reduce the amount of typing you do, but they're equivalent under the hood. The inverse of concatenate is split. So just as you can combine arrays into one, you can also split them. So here we're taking an array and we're splitting it, and now you have to pass the breakpoint. So we're saying split this array at positions 3 and 7, and so you get back 3 arrays, basically slicing or splitting at position 3 and 7, and so it gives you back 3 chunks. All right, let's say, I guess 5-minute break. I've noticed that many people seem to be hanging around during the break, so feel free to take longer if you want. I'll start it in 5 minutes, so 10 a.m. on the West Coast. Feel free to ask questions during the break, and I'll answer them. We're actually making reasonable time, so I think we probably will get to go through the stuff in this second notebook, which gets a little more advanced, not much more advanced, but I think it's sort of beyond the very basics. questions? I'm going to take this as a sign that everything I say is super clear. I see someone raising the hand. You can just ask a question, unless for some reason you can't. I think you should be able to. We're not. I guess I'm actually not sure that we're set up to let people speak, but you can certainly ask your question in the Q&A, or in chat is fine too. Oh, sorry. It's kind of a very strange way of interacting when you're talking into the void and there's no facial feedback or anything. But please do provide feedback if there's anything that I could do better or differently. Sometimes people say I should speak slower, and I try, but then I forget and I speed up again. So I apologize. Okay, let's start up again. So hopefully you can all still see everything. All right, let's talk about mathematical functions. Actually, at this point, almost everything else we have left doesn't really introduce any new concepts. So we're not introducing new indexing conventions or talking about restructuring. We're sort of just now in the land of you have a whole bunch of functions in Numpy. Where are they and what do they do? And so I'm really just going to pull out just a couple of examples. But I do encourage you to just scan the various modules in Numpy just to kind of get a qualitative sense of what's available. And then when you need something, you might remember, oh yeah, sure, there's like this whole module, linalg, that has like a whole bunch of linear algebra functionality. But let's start with just like simple arithmetic. And so this will not shock you at all if you've done any kind of array computation in R or MATLAB. So I have an array. I can multiply it by 2, just like I would if this were like an integer or float. And what you get back is another array with the same dimensions, and the arithmetic operation has been applied to each element in that array. So this is called element-wise operation, which means the same operation is being applied identically to every element in the array. And all the arithmetic operators in that Numpy supports have this flavor. They all do element-wise operation. So just to show you that, here's a whole bunch of operators applied to this one-dimensional array. And so we can add a number to an array. We can divide an array by a number. We can use the modulo operator to get the remainder. We can raise every value in the array to some power. No, nothing should be terribly surprising here. Just be aware that there are languages in which like this might be interpreted, for example, as matrix multiplication. But the mathematical operators in Numpy are always element-wise. They will apply the same operation to every single element. And if you want to do matrix multiplication, then we'll talk about that momentarily. So you have to do that in a slightly different way. Okay. What about operations where the two operands are not well, it's not one array and one number? Can you have two arrays? Yes, you can. For example, you can subtract one array from another. The key is that they have to have the same shape. And again, well, actually, yeah. There's some subtlety there, and I'll talk about broadcasting in a bit if we make it that far. But the idea here is you can apply any operation involving two arrays. Any mathematical operator, they just have to have the same shape. You can also perform what are called in-place operations using these operators. So often you'll want to increment an array by, let's say, 1, right? But you don't need to create a new array. You just want to change the array you're already working with. And so if you add the equal sign to any of these operators, then that will update the array in place. It's essentially shorthand. So this expression x times equals 2 is shorthand for this. It's doing exactly the same thing. It's just as if you multiplied on the right hand the array and then assigned it back to the same variable. So that's convenient. Okay. Yeah, sorry, now we get into like just spamming you with a whole bunch of functions to do all kinds of things in the Numpy library. So the first thing is to note there are all of the standard mathematical functions. Many of these sort of map cleanly onto, so there's a math module in Python that has lots of mathematical functions, but they only operate on individual numbers. And now you have sort of equivalent functions that operate efficiently on arrays. And so, for example, you can take the absolute value element-wise for any array. You can take, in this case, the natural log of all the values. There's support for all of the standard trigonometric functions, and lots of other stuff that you can find. And okay, let's see. Yeah. Okay. So yeah. So whoever some comment earlier was correct. It just is slow. And so here, if you want to see like all the attributes available to you just in the root NumPy namespace, this is without importing from modules underneath the root namespace. You can see that there's a lot there, and so you can just leaf through this, and there is just there are lots of things you can do with NumPy arrays. And we're not going to have obviously time to talk about almost any of this. Okay, let's talk though about some of the critical aggregation summarization functions, because you will probably use these a lot. So these are mostly unary functions, which just means they take a single array as an argument. Like a binary function would take two arguments, etc. And so here we're constructing a simple one-dimensional array, and the sum function will give us it'll give us the sum of all the elements. No surprise there, right? This probably is exactly as you would expect. And similarly for max, min, mean, median, variance, etc. They all operate exactly the same way. You can also apply, however, functions along an axis. So this is all one-dimensional. There's no ambiguity about what you would sum over if you only have a one-dimensional array. Right? Obviously, you're summing over all the elements in that array. But if you have two dimensions, it becomes ambiguous. When I say sum on a two-dimensional array, what is it that I expect? Do I want a sum of all the elements? Maybe it's 10 by 10, but I want the sum of all the 100 elements. Or do I want the sum along the row axis or along the column axis? And so we can specify that. And so here I'm starting with a one-dimensional array, reshaping it into a two-dimensional array, 20 by 5. And now I'm printing the mean over either the first axis or the second axis. And I do that just by, again, calling mean, but now I pass this argument axis. So if I say axis equals 0, then I'm going to have to get the mean over the columns. So this is basically telling NumPy that we want to apply the operation along this axis 0, and in this case along 1. So you can see the difference in dimensions, right? So when we take the mean over the columns, the result has 5 values. But if we take it over the rows, then we have 20 values. So that's quite helpful because it means you can indicate for a potentially high dimensional array which way you want to aggregate over. NumPy also has plenty of linear algebra functionality. So this actually came up already, right? You can create an identity matrix. You can invert matrices. You can also take the pseudo-inverse. There's all kinds of stuff in there. There's SVD, there's eigendecomposition, like pretty much everything you would expect from a linear algebra library. You can do matrix multiplication or taking the dot product. In this case here, I have a 2 by 5 array and a 5 by 2 array. So for those of you familiar with the rules of matrix algebra, right, this should get, if I multiply x by y, I should get a 2 by 2 result, and that is exactly what I get. Again, there's lots of stuff in pretty much everything I've showed you can be expanded indefinitely. There's lots of stuff to talk about. So I would encourage you to go and look at the linear algebra library if that's what you're looking for. If you're coming from MATLAB and you just want to know, well, how do I do the equivalent of this, then you will almost certainly find an answer quite quickly. Okay, so we're actually making good time. That's good. So, all right, so where to next? So that's just the very basics of NumPy. We're just scratching the surface. I will, in a sec, go on to the second notebook, which has a little bit more, a couple of more advanced concepts that are really good to be aware of. But I would strongly recommend, I mean, there's lots of tutorials out there. I think probably the best one, or one of the best at least, is this NumPy chapter from Jake van der Plas's really, really excellent Python data science handbook, which is free online. Although if you like it, I would really recommend that you maybe buy it and show your appreciation. The whole book is really fantastic, and that's usually where I point people to. It's longer for sure, right? So it'd probably take you several hours to work through that chapter, but I think that's a really good place to go after this. So let me talk a little bit more about NumPy, and then I'll come back and talk a little bit about pandas. Okay, so everything I showed you is like really critical for being able to work in NumPy, and if you just follow that link, it's Python, or you can just Google Python Data Science Handbook. Someone just asked what book that was, and it's freely available online by Jake van der Plas. Okay, so everything I talked about was sort of basic, and that's not to suggest that the stuff I'm showing you now is not important. It's also these are also sort of concepts that you will probably invoke on a daily basis if you do a lot of work in NumPy. And the first one is broadcasting. So actually, let's start by importing stuff again. So broadcasting is super important, although often it will be done for you fairly invisibly. And so you may not even notice that it's happening. And so remember, I started, or a little bit earlier, I said that when you, for example, assign a replacement array to a subarray in another array, the shapes have to match, right? So if we have that, remember that 5 by 5 array of zeros, and we replace part of it with ones, and I said that these have to match. And that's true more or less. Like if you tried replacing this with some arbitrary shape, probably wouldn't work, because you can't, it will tell you, I can't broadcast input array from shape 3, 2 into shape 3, 3. Okay. But that does not mean that these shapes have to perfectly match. And in fact, they don't. If there is a way to essentially repeat one of the arrays along one axis several times to get the target shape, which is called broadcasting, then the operation is actually perfectly legitimate. And to show you the most trivial example of this, I kind of mentioned this already, you can always replace any subarray of any size with a single value. Like I could always say, I didn't, this is sort of like, it's kind of silly. I didn't have to create an array of ones just to say that I want that subarray filled with ones. I could have just said, make that one. And what's going on implicitly is you can always basically expand that one along the axis you need to get it to fill up the space. And so that works. But you can also pass arrays that sort of expand or broadcast to match the target. The rules of broadcasting you can find if you click on this link, and you can read up about them. I don't want to spend too long on them. Actually, this I already mentioned. You can always replace any set of values in an array with a single value. I will note here, we're introducing this special value nan, so that just stands for not a number. If you've worked in other numerical environments, you will be familiar with this concept. It's a special value found inside the NumPy module, and so in this case, we're replacing the zeros with nans. And so there are lots of operations in Python, in NumPy, where if you tried to pass in an array containing nans, either the operation would fail, or you would just get nans back. It would just silently ignore them, and that can be quite helpful, right? So there's many reasons why you would want to have in your language a way of representing the absence or the invalidity of values. The second script is accessible. Sure, you can just click on there. If you don't see it, then it's probably because I added a little bit later. So I apologize. So again, you could, as I mentioned earlier, you have to restart your hub essentially. So if you go to File, Hub Control Panel, and then stop my server, and then start, and that should bring it up. So if you have the first but not the second, that's probably why. Sorry about that. Okay. All right. Let's talk about more advanced indexing. So far we've been indexing arrays entirely with individual indices or with slices, but you can also index arrays with arrays. And this, I will warn you, gets conceptually messy. And if you ask questions, which I encourage you to, I may have to stop and think about it for a little while because it can be a little tricky. So I'll show you a couple of examples. So let's say we have a one-dimensional array. So here's our array, and we want to index this array. Okay, these are just the squares of the first 8 numbers. And we want to index with this 2 by 2 array. Okay, now that might seem puzzling on the surface, like how could you index a one-dimensional array with a two-dimensional indexer? What does that mean? But the critical point about this is the numbers inside, the numbers here are not, they're not, or sorry, they're still the indexes in that original array, right? So there's only one dimension. So all of these numbers are basically saying within that one-dimensional array, give us the value at index 2, the value at index 6, the value at index 1, the value at index 3, etc. And so when you're indexing a one-dimensional array with an n-dimensional array, the shape of the indexer is actually telling you the shape of the result you want. So this is essentially saying if I index with, just maybe to make it, oh, sorry, this is where I'm printing the actual result of the indexing, right? So when I pass that two-dimensional array as an index, I'm saying I want the output to be a two-dimensional array, but the values are indicated by the actual individual indexes, which correspond to the positions in that one-dimensional array. That may be confusing. It is fairly confusing, but hopefully you can see how that works. Now, generalizing that, this gets a little trickier. What happens if you want to index a two-dimensional array or an n-dimensional array with another array? So now this gets a little more complicated. So here I'm constructing a 4x4 array. And so you can see the array that I'm going to be indexing here. And now this will be a little counterintuitive. So now notice I'm constructing, well, actually, before I do that, let me show you what would happen if I constructed a 2x2 array and just passed that as the indexer. So maybe you're expecting now you'll get back again a 2x2 array, but you don't. You actually get back a 4x2 array. And the reason is that now these values are interpreted as, in this case, the rows of that. They're interpreted only as the first axis in that array that you're trying to index. And so you actually end up pulling out more values than you expect because each of these is actually pulling out multiple values. Instead, if you want to get back a 2x2 array, the kind of thing to be aware of is that when you're indexing a two-dimensional array, you need to pass two indices. Right? So you have to pass something in along the first axis and also on the second. And so what we end up doing here is constructing two separate arrays. These are two separate 2x2 arrays. And so now, and actually let me print. Okay. So you can see this. There we go. Okay. I just realized this is going to be hard without being able to actually point at things, but I'll try to use the cursor. So so we have these two separate arrays, and this whole thing is getting passed in as the index along the first axis, and this whole thing is getting passed in as the index along the second axis. And so if you want to kind of understand how this result comes out of this array, observe that what's happening is the first value here is actually getting taken from, so this is the value along the first dimension, right? So this whole thing is indexing the first dimension of our two-dimensional array up here. All these numbers are always referring to the first dimension, and these are always referring to the second dimension. And the shape of these two things, which matches, tells us the shape of the output. And so we're still going to get a 2x2 output, but each value in each element in this 2x2 output, you kind of have to imagine like, you can imagine maybe stacking that first 2x2 array and then the second 2x2 array, and then kind of going this way through that, right? So the actual position of the element we want here is given by 0 in the first axis and 1 in the second one. And for this 13 comes from the index 3 in the first axis and 1 in the second axis. Right, and you can see that's where that's coming from. That may be very confusing, and it takes a little while to wrap your head around that. But it's good to work through that to understand that, because lots of stuff builds on that. And Boolean indexing or logical indexing, for instance, what we'll talk about in a second, kind of relies implicitly on that. I will note that in practice, very often you are actually just passing. So if you have one array and it could be have as many dimensions as you want. If you have a two-dimensional array and you're passing as index an array of this exact same shape, then that will be interpreted in this Boolean indexing case I'll talk about in a second as like a one-to-one map. So it's just like you're saying, like, do you want the value here or not? So actually, this is a good segue to Boolean indexing. This is actually not super common. Like, it's not actually that common to do, or at least in my experience working with neuroimaging data, to index arrays with explicit multi-dimensional arrays. But Boolean indexing is extremely common. So this is really important to get. So let's reload that image we were using a bit earlier. And now what we're going to do, and this will answer one of the questions that came up directly, I think. Now what we want to do is we're going to filter that image. So suppose we know that there are values. In fact, I'll just show you. So I'm just plotting a histogram here. This is the histogram of all the values in the image. And as you can see, like, the vast majority of them are 0 because most of the volume is empty. The brain is only at the center of that image. And then you can see that there's this distribution of non-zero values over here. And you can see the mean looks like it's about 6,000. So let's say for whatever reason we decide we just want the values above 7,000, right? We're filtering that image and we're only keeping the values above 7,000. Everything else we want to turn into zeros. So first thing we do is we apply this logical operation. We can always just say like data greater than 7,000, which is interpreted as you can think of it as like, it's a logical operation that's going to be applied element-wise, right? So remember, all operators get applied element-wise. And so at every point in that image, what's being asked is the value greater than 7,000, yes or no? And the result is an array with the same dimensions as our data array, which is being spit back to the screen here, but we'll store it in this isBig variable. I'm just calling it that because that's really the meaning of it. We're just like, we want some place to store information about whether or not the value exceeds some threshold we consider large, let's say. Okay, so now we have a Boolean array isBig, and let's just verify that it has the same dimensions. We can ask, does this have the same dimensions as the original image? And the answer is true. Yeah, so it does have exactly the same shape because the logical operation applies element-wise. Now what we can do is we can use that Boolean array to index the original data array. So we can do this, and you can see this construction over here where we're just passing isBig as the index to the original data array. And that will succeed, right? So you don't get any error. And if you look at the shape, that now, interestingly, this is not the same shape. Okay, so what's happening here? Now what's happening is that when we pass this logical index, at every value in that image, at every element, if the value is true, it's going to be returned. If it's false, it's not going to be returned. But it is returned as a single one-dimensional array. Okay, and so big values will just look like an array. Notice that there's no zeros here anymore. In fact, we could plot a histogram of this and you would notice that, just verify that there's nothing below 7,000 here. I'm not going to explain the plotting because remember, there will be a separate talk entirely about plotting. So there's the histogram, and sure enough, we can see that the smallest values are 7,000. So that seems to work okay. But this is not terribly helpful to us because we don't want this one-dimensional array. We want to be able to visualize our image probably in the same space we had it originally, but with the low values gone. So if we ask, what is the shape of this? Great, we know that there's 50,465 voxels in the image with values above 7,000, but we want to put that back in the original shape. And one way to do that is the following. We can start, let's just copy the original image because we don't want to modify the original image. We might want to return to it later. So we'll create a copy called filtered, and we can just use the copy method of every ND array, which will return a copy of itself. And now what we do is this. We again pass this isBig array. So remember, this isBig has the same shape as filtered. And we say that for every value where this evaluates to true, right? So every value that evaluates the true inside this expression here, inside the square brackets, we're setting to 0. Notice this little squiggle. What is the tilde doing here? That means not. So that's just a negation. And so if we don't have the tilde, what does this say? This says that we actually, for every value that currently is true in this is big array, we want to set 0. But that's not what we want. We actually want the opposite, right? We're saying, no, for every value that's false, we want to set the value 0. And so not just negates that array. It turns every true value into false, every false value into true. And so if this all worked as planned, then we should see, well, first of all, the shape is unchanged. Right? That's good. But now let's actually look at what happens here when we run this. And we're just plotting the original slice along the new slice. And lo and behold, what you're left with is mostly white matter, because white matter has higher intensities than gray matter. At least in this T1 image. And so that's nice, right? So you've done some filtering, and this actually just like out of the box, this was not by design, but even just that's almost like that's a pretty reasonable separation of white matter from gray matter, right? You probably want to do something a little bit cleaner than this, but even just like that hard cutoff saying like everything about 7,000 is white matter doesn't look completely crazy. Let's see, there's a question. So how are we going to define the boundaries of our brain image that 0 values are not included? Well, so just to clarify, you can't, I mean, the n-dimensional array is always going to, it's going to be rectangular, right? You can't have an array that's sort of just exactly the contours of the human brain. And so you'll always have zeros like around the brain. What you could do potentially is you could like shrink that bounding box so that it only just like basically it's the smallest box you can have that still contains the brain. I won't go into that because frankly I have to spend a little time figuring out how to do that. It's probably a few lines of Numpy code. It can certainly be done. But you will certainly still have zeros in the image because there's going to be empty values in that space. I mean, you can set them to NaN if you want. So if the concern is that you don't want to confuse like meaningful values with like, you can represent missing values with NaNs, and that would be as simple as doing, so you can say, you could certainly say, there's an isNaN function, right? So you can say filtered I'm sorry, we're going to, so filtered equals 0, and then you can say, well, turn that into NaN. And I'm not even sure if this will plot. Okay, so that's what happens, right? So now 0, because there's missing values, it's in the plot actually interpreted as, it doesn't get assigned a color because it's not actually a value. So yeah, so you can do that, but yeah, you are always going to have some value in the space around the brain because the array has to have rectangular dimensions. Okay. All right, and then the last thing I have here, I mean, this is still just a small fraction of what's available in Numpy, but I did kind of want to note a couple of tips and tricks, just things to be aware of. One of these I kind of already talked about a little bit earlier and also yesterday, which is vectorization. So Numpy arrays are iterable structures. They're sequences. You can always loop over them. So, here's, you already saw element-wise arithmetic, right? So I'm creating a new array and then I'm adding 2.2 to every element. But I could have explicitly written this out in a for loop like this. So I loop over every element and I update the value. So I could do that. And you might suppose naively these are just equivalent. They're just different ways of writing the code, but they're doing the same thing. So they should be equally fast. And the only reason to prefer the first is it's less typing. But no, actually the second one, not only is it more typing, it's actually much, much less efficient. And the reason is because, as I alluded to, because Python is a dynamic language, when you write it the second way, it's actually doing a lot more, there's a lot more overhead involved in pulling out each of the elements, looking at it, figuring out what type it is, and then doing what you want, and then putting it back into the array. Vectorized operations, because they're NumPy structures, and NumPy actually under the hood uses C for most of what the heavy lifting. That's all sort of mapped into a C data type for you. You don't have to actually, there's no overhead involved in looking and inspecting each element. And that really adds up quickly. So in NumPy, which is not true of all languages, but in NumPy, you are almost always going to be better off vectorizing your code. So if you have loops in your code, try to figure out a way to avoid that. Try to apply the operations over entire axes of the array at once. If you see a for loop, there's a good chance that getting rid of it would speed up processing. That's not true in all languages. Like in compiled languages, like for example Julia, this would be probably actually faster than if there's, I don't know Julia or if there's an equivalent, but that would be fine. Right? You'd be going as fast as you can if you construct at least certain kinds of for loops. But in NumPy, that is a bad idea. So you want to make sure that you avoid for loops whenever possible. Not always possible, but often it is. A second thing to be aware of, and I kind of mentioned this earlier, is there's a distinction between copies and views. So most NumPy functions will return arrays that are derived in some way from other arrays. And most of the time, the result will be a completely new array. And the arrays that went as inputs are not modified. So for example, here we create a new array, assign it to x. That's the value of x after the assignment. And now if we multiply x and assign that to a new variable y, x is unchanged, right? So notice the value of x here remains the same. Yes, we multiply that x array by 2, but we assign that result to a new variable, and it doesn't automatically modify the existing variable, which is good. Wouldn't want to just like overwrite existing variables every time they're involved in a transformation of some kind, even implicitly. The thing to be aware of, though, is that this is not always true. There are operations that will not return a copy. They will return something called a view. And a view is basically kind of like the name suggests. You can think of it as sort of like a different window onto the same data, sort of a different way, a different lens, a different way of looking at that data, but you're still, in some sense, connected to the original data. So here, what you'll see is we create an array, a 4x4 array, and when you slice, when you index an array using this syntax, just to kind of show you what this is, first of all, right? So I create a 4x4 array, and then I take a slice, a 2x2 slice, and return it. Okay. But if I set a value on that subarray defined by these indices, I set them to 1, and now notice what I'm printing here is the original x, right? So even though we assigned a new variable here, view x, and we only modified that, we thought, if we look at the original value, we'll notice that x has actually changed. Okay. Why? Because slicing or indexing returns a view. It doesn't return a copy. It returns still attached to that original data. And that's desirable most of the time because it means that you can construct lots of different views and you can apply operations to subsets of the data without having to create a new copy every time. Like you would eat a lot of memory up in many cases if every single slicing operation created an entirely new copy of that array. But sometimes you want to modify that, and you need to realize that you are actually making changes. If you modify a view, you are modifying the underlying data. And so what you could do if you needed to modify that without touching the original is just called copy. So you can copy that array, and now that has no impact. All right, last point I want to note, and then we'll switch to talking about pandas a little bit, is the syntax. So if you aren't coming, or you don't have a lot of background in Python or another object-oriented language, you might have noticed that a lot of NumPy, well, not a lot, so sometimes we've been calling things like, if there's a question about this, like, .t, which is a different syntax from something like zeros, right, where we pass an argument. So there's a difference between like this functional syntax where we're invoking a function with arguments versus this object-oriented syntax where we might say something like x dot something, x dot t, for instance, transpose. And I covered this yesterday in my Python presentation. So if you're not familiar with object-oriented programming, you could go back and look at that. The thing to note, the only thing I want to note here is that for the sake of convenience, NumPy does give you object-oriented access to many of the most common functions. And so a lot of the functions that you've seen already could be written in object-oriented format. So like, let's take that, well, here, let's create a new array. So if we have something like a random array, and remember, if we want to take the mean, we can do something like this. So this will give us the mean of, screw up. Oh, sorry, this is, okay, so this is taking the mean of that array along a particular axis, but we could equivalently write that as x.mean axis equals 1. And so this it's not entirely identical, but essentially this is the same thing. You're writing the exact same thing here. Oops, okay. And so that's just for convenience. And sometimes it is, as you saw, it's easier to write x.t than to write np.transpose of x every time you want to transpose x. So the reason I mention is because even if you stick purely with the functional syntax, you will see things like this in the wild. So when you read other people's NumPy code, and don't be surprised if you see this, and like all it means is it means the same thing as this. It's just a different way of accessing the functionality. Okay, let's see, there's a question. Is R an object-oriented language? No, R is definitely not an object-oriented language. R has actually 3 object-oriented systems, but they're not really object-oriented. The language itself, it's sort of like it's slapping onto a functional language, like something that looks like an object from the outside. That doesn't necessarily carry major implications, right? I mean, you can write perfectly good object-oriented, well, perfectly good is strong. You can write object-oriented packages in R, and they will behave more or less as objects do in many other languages. But the fundamental, like the data model underlying R is, Python is quite different from the way things operate in R. In Python, everything is an object, and in some sense, ultimately, even when you're calling functions, functions are objects, right? So it goes much deeper in Python than it does in R. So yeah, I would not describe R as an object-oriented language, though it does have object-oriented functionality. Okay, let's go back to that first notebook. And in the time remaining, so I mean, I do apologize. I kind of was torn when developing this. I didn't know whether to spend more time on NumPy or Pandas, and I opted for NumPy mainly because it's kind of hard to understand what's going on in Pandas if you don't if you don't have a sense of like n-dimensional arrays, for instance, at least 2-dimensional arrays and indexing. And Pandas is also kind of a different beast in the sense that there are sort of maybe fewer big concepts to get, but there's it's a much broader library in the sense that there's lots and lots of little tools that are super useful, but there's just no way around the fact that you're going to have to like learn what all the little things are in Pandas that do what you want. Whereas NumPy, I guess in a sense I would say, is more principled. Like there's a lot of functionality in the various modules, but there's sort of a small number of core concepts that will let you figure out, I think, like how things work more or less. But the nice thing is that Pandas is extremely widely used, and there are fantastic resources. And again, once again, we'll recommend, if you have the time, I very strongly recommend working through Jake van der Plas's Pandas chapter in his free online book. And it is available as a series of notebooks. So if you click this link here at the bottom, Open Colab, that'll actually open these notebooks in Google Colab, which is a kind of derivative notebook derivative type of project, and lets you run in real time. It's a little similar to our hub, actually, lets you interact with that. So, and actually, Jake now works on, I believe, on Google Colab. So you can actually like be dropped into Google Colab and start interacting with these Pandas notebooks right away. So that's kind of cool. So I would encourage you to do that. I'll just show you a little bit of the functionality in Pandas just to give you a flavor. There's a question, are there more rules, tricks we should keep in mind when writing code to optimize them? Yes, probably lots, but those, I mean, I can't think of any sort of like big ones that would apply like very generally. I'm sure there are. They're just things that come with experience. You'll just learn over time, like, oh, this is not a good way to do this, I'll do it this way. And to some degree, a lot of that is often arbitrary. It's just like what happens to be like optimized better in this environment than in another one, right? There are operations that might be faster in NumPy than in MATLAB or vice versa, not for any good reason except that like the developers spent more time optimizing that. So a lot of it is just experience. Chris has a, okay, yeah, so Chris Markevich has an answer there. I missed live answer, I can only see the first file. Yeah, so I'm sorry, if you only see the first file, not the second, you'll have to restart your Jupyter Hub. I just posted that a little bit later, so I apologize for that, but if you restart your hub, you will have that show up. And that will be true the rest of the week. If something doesn't show up, and clearly it should, then just assume that you need to restart your hub. At this point, there's not much left, so you might want to just hold off and just do it afterwards, but it's up to you. Okay, so I'll just give you a few examples in Pandas, and feel free to ask if you have specific questions, like how do you do this, and hopefully I can show you in time remaining. But just to give you a very brief example. So the first thing we'll typically do is read in data, and Pandas has this like workhorse read CSV function that will handle pretty much anything you can throw at it if it's tabular and it's plain text. It has, I'll just show you, there's many arguments. I think it's being slow because, oh, sorry, it's because I haven't imported it. Right, like to run the cell. Okay. So you can see that there are lots of arguments to read CSV that will change behavior. So you can, there's a good chance that you can read almost anything in plain text as long as it's structured in tabular form. All we're doing here is we're reading a data set. This is actually abide data for those of you familiar with the abide project. I'll be using this as a running example tomorrow in the machine learning tutorial. So I won't talk about it now, but we will read it in. So we're just reading it in. And head lets you inspect the first n rows of the file. So here's what the first 5 rows look like. And one thing that's nice about the Jupyter Notebook is it sort of nicely formats Pandas data frames. And that's what this data type is. So the kind of core data type in Pandas is a data frame. And the data frame is essentially a wrapper around a Numpy array. So if you access the values attribute in a data frame or a series, which is the other sort of big or sort of major data structure, you will actually just get back an array. So you will get back the Numpy array. So you can always pull out the actual Numpy data from a Pandas data frame or series just by asking for values, which is nice because sometimes you will want to use sort of raw Numpy and you don't want to mess with all the other, like the Pandas layers. The reason that the Pandas is so helpful though is it adds to that core Numpy functionality just a ton of utilities for working with tabular data. And so and also gives you essentially a better version of structured arrays. It gives you named columns and rows. So if you're used to R, you might wonder, well, why can't you name columns in NumPy? And you just can't, although there are structured arrays, which are kind of a pain in the ass to work with. But Pandas will give you the equivalent of what, essentially, Pandas' data frame is equivalent to a lot of the functionality in base R's data frame. How do you index in Pandas? This is sort of a pain point. It's a little confusing, and I always feel sort of a little defensive because R's data frame indexing seems a little easier when you see it. You don't have to like worry about these like iloc and loc indexers. There is actually a good reason for that, which is that R's indexing is quite ambiguous and can get you into trouble. And so Pandas does force you to be more explicit. I don't have time to explain exactly why, but you can read up on that. But the main thing to be aware of is there's mainly kind of 2 ways to index in the Pandas data frame. One is by integer location, so the position. And those would, just like you would in a list or a NumPy array where you're giving the numerical position of the values you want to pull out. So what I'm doing here is I'm pulling out all of the rows and only the first 6 columns of that data frame. Oh no, I just did something. Okay, there we go. And this describe method provides some nice summaries of numerical variables. And so I can see the count, so how many rows there are, the mean value, standard deviation, minimum, the value of 25th percentile, 75th, et cetera. That's just a nice way to summarize the data. I can pull out individual columns. And this, so I mentioned that indexing is a little confusing. This is, part of the kind of confusing part is that you can see this and you know, clearly you can access some slice of the data with just by passing the name without this like iloc thing up here or loc. This is equivalent to doing this. And so the difference between iloc and loc is the I means you're passing numerical index, like the order, the position, whereas loc is by name. It's the named index. And so if you have a column named age, sorry, my laptop is screaming at me for some reason, I'm having some issues. Oops, sorry. If you use loc as the indexer, you need to pass in both axes. So this would basically say, give us all the rows for the column age, but for shorthand, you can just say this. Now, it is hard to avoid the shorthand because you type less, but I will say, particularly when you're new, despite the fact that it's a pain in the ass, you might want to, just to get yourself oriented to what's going on, you might want to force yourself to stick with these iloc and loc indexers that always require you to pass in both. Well, they don't require it, but you probably should pass in both of these, right? So you you basically are specifying exactly the values you want along both axes. Once you get comfortable with that, then you can sort of look up the cheat codes, basically. And you can index along both rows and columns. So here, I'm asking for the rows with the label 2 and 5. I picked a bad example. I kind of wish I hadn't done this, because this is just going to be more confusing, because these look like numbers. So you might think these are like numerical indices, but actually the labels, the indexes of these rows just happen to be numbers. They didn't have to be, right? They could have been strings. So I apologize. This is probably not the best example. Anyway, let's not worry about indexing. This is partly why I didn't want to talk about pandas, because it really takes sort of a good 20 to 30 minutes just to get clear on indexing in pandas. It is very powerful, but there's a learning curve. Here's how you might sort data. So there's all kinds of things you can do with the data frame. In this case, we're sorting that data frame on multiple columns, first group. So we sort just as you would in, say, Excel or something else, right? You sort first on that first column group, which is diagnosis group, autism, or control. And then within that, if there's, within each of the levels of that group, we would further sort by age. So if we look at the first 10 rows of the result, you can see that now all of the rows are group 1, because there's many, many rows. And then within that, you can see that age increases monotonically, right? So these are very young children in this case. These are 5-year-old children. And one is autism. So these are the observations that are very young children with autism. So we can sort data. We can do much more sophisticated things. So here, let me just kind of show you what this is real quick. So this is just like one line, although really it's a compounding of several statements. What we're doing here is we're taking the mean values of the first 5 columns whose names start with FS area. These are free surfer features. They're surface area of ROIs. I'll talk about this data set more in the machine learning tutorial. But let's break it down step by step. What we're doing is we're taking that data frame, filter pulls out columns or rows, in this case, columns that have certain properties. In this case, we're saying that their name has to be like is a SQL convention. Just means that the name has to contain or has to match the string FS area. And then we've already seen indexing. We're taking the first 5 rows, and then we're taking the mean of that. And if this is confusing to you because you're not used to object-oriented syntax, we could have done this the following way. We could have said, so I just want to kind of make it clear that all that's happening here is we're stacking these lines. Right? We're writing it as one line of code, but it is no different than sort of assigning every intermediate step and then producing the output. Okay, and the last example I want to show you is really cool, and this is, I mean, this is not unique to Pandas by any stretch. In fact, I think it came out of R. It is a strategy called split, apply, combine. And the idea here is that you are taking some data frame, you are grouping it by one or more variables, you're applying some function, and then you're going to bring back the results and concatenate them so that you have a summary. Potentially, it doesn't be a summary, it could be transformation, but this could be a summary of every group separately. And so that's really, again, we could have written this, just to kind of show you, we could have written this all in one line. What we're doing here is we're taking the variance of a particular column, but grouped separately by every combination of sex and group in the data set. So here we're constructing this grouped by object in Pandas, which is just sort of like, you can think of it as a temporary placeholder that it's like a grouping that gives you functionality that operates on the groups. So we construct this grouping variable by saying we want to group the data by sex and group. We could have other columns if we wanted to. And then we're pulling out just one column from that group by variable, and we're calling var or variance on it. Right? So, and these are all little shortcuts. You can write this more explicitly, but the point is just to show you that you can do like really sophisticated things in essentially like, 20 or 30 characters. If you were to do this in like base Python, working with like lists and dictionaries, you would probably have to write like, depending on how efficient you are, right? But minimum of several lines of code. And an inefficient implementation might take you like 20, 30 lines of code. And so, and this is also going to be much faster for many of the reasons I said Numpy was faster. It's highly optimized internally. So here you're seeing that just in that like essentially 1 or 2 lines of code, we are breaking down the variance separately for sex and group for this one column in the data set. So Pandas is incredibly powerful, but it is a sort of very broad API, so it takes a little while to sort of really learn it well. Once you do, you'll be able to do really sophisticated things with your data in very little code. All right, so we have like 5 minutes left. Actually, I don't think there's anything after, so you know what, I will run until 1 p.m. my time, 11 a.m. Eastern. Feel free to leave sooner, obviously. So I will just take questions for the rest of the time. Does like equals basically operate like grep or pattern matching function? Not quite. It operates, I believe, the way like would in, you can think of this as like being the equivalent of this, right? If you're used to like Unix blob-like syntax, it basically just says that the name matches on either side. Now, you have other arguments to filter, like you actually do have a regex argument. So if you know what regular expressions are, then you can do much more powerful things, right? So I could have said something like this, you know, and if you don't know what this looks like, don't worry about it. But if you do know, like you can pass arbitrary regular expressions, and that will, in this case, pull out exactly the same columns. And there are also other, I forget, you can also, I think, specify, not actually sure what. Oh, okay, so items is just a way of like, it's giving it it only returns values that are in that set. So you have various options. And there's other ways to select columns too. I mean, there's lots of flexibility in Pandas. And the general tip, right, is like anytime you want to know, like you can pull up the documentation with Shift Tab, or you can just do something like, you need a little more information that you can prepend with the question mark, and then you'll get the whole doc string from the documentation as output. Yeah, the answer there is correct. You can use tail; it's the equivalent of head. Can we coordinate participants' information from fMRI onset times and reaction times? Type of fMRI data as a result of self-fuzz to Pandas. Yeah, so good question. And actually, I think I have this in a comment up here. Pandas actually does have a read Excel function you can use. It's not perfect. So Excel files can actually be pretty wonky. They can have like all kinds of weird formatting stuff. So it may not always read Excel correctly, but most of the time it's pretty good. So if you use read Excel, there's also read SAS, read SPSS, etc. So Pandas really can handle a lot of different formats out of the box. Beyond that, of course, you can always export your data to a tab delimited file or just some other form of plain text file and do it that way. Any other questions? Still have 10 minutes or so. Like anything at all, if there's any manipulations. I mean, I can also, if people are sticking around, I can also, let's see, what else can we? So that general split apply, is there piping in Python? There is, well, there have been proposals for piping. I'm not sure if there's actually anything on the books right now. There is something like piping in Pandas specifically. And I'll probably get this wrong because I almost never actually use this. I don't think I've ever used this really, but I know it exists. It's not piping in the sense of like being an operator like that. And the reasons for that are technical. There have been long discussions about it, but there is a pipe. I will probably mess this up. Okay, yeah, so I don't actually remember exactly how it works off the top of my head, because like I said, I don't tend to use pipe. But the conceptually that is the same. It's a little more typing because you're using this pipe function, but you can essentially like stack functions. Keep in mind though that a lot of what the piping does in R is already achieved by the object-oriented syntax, because every time you call a function or a method on a data frame, or very often you'll get back a data frame, and so you could just keep appending dot, et cetera, et cetera. And so that's the place where Python's object-oriented nature actually, in some ways, already does the job, sometimes at least, that pipes accomplish. You can just sort of stack statements one after the other and via like this object-oriented syntax. Can you get the variance for the one specific column title? Can you do this for multiple columns at once, e.g. with wildcards? Yeah, so that's kind of what I was showing you there. If you're asking, can you like implicitly average over them, you would have to, there would have to be an extra command there. So you can think of that as like, first you select the columns you want. You can use a wildcard with the regex thing I showed you a moment ago with filter, for instance. And then you can take the mean over, well, actually I take that back. You can get the variance over multiple dimensions. You can also use Numpy to do what's called, to unravel the internal Numpy array. So the answer is yes. And in fact, there's several ways to do that. And that's true of many things in Pandas. In fact, I've had experience many, many times, and I've been working with Pandas for a long time now, and I use it a lot. But I still fairly regularly come across like little snippets of code someone else wrote, and I'm like, what does that do? And I think I might realize that it does something very clever and more efficiently than something I do fairly often in a more cumbersome way. So there's lots of little like tricks and many ways to do things of the kind you're asking. It's just a matter of, there might not be like one function or one method for it. You might have to stack 2 or 3 statements. Practically speaking, NumPy and Pandas can make using things like FSL Math and Shell more obsolete, right? Yes, absolutely. I have not used, well, to be fair, I don't do very much analysis of actual like time series anymore anyway, but yes, I think that you have much more flexibility. You're not calling the shell constantly. There's less typing. I think there's many reasons why if you can, you probably want to avoid doing, and you also, it's much easier to write custom code, right? Like you don't want to have to write like your own shell scripts to kind of provide additional functionality if you could just write one or 2 lines of Python code. So yeah, I do think that to the degree that you're able to get what you need to do into Python and into Pandas, you probably are better off for it. Having said that, we are not yet at the point where especially on the statistical estimation side, there is really nothing that provides all the functionality of FSL, right? So like, I don't even know if we'll cover it. There's like the most widely used Python package is for fMRI estimation is something called NiStats, which is actually now in NiLearn. Actually, maybe, I'm not sure if Elizabeth will touch it or not, but it's very, I don't say impoverished, it's quite fast and it's good at what it does, but it doesn't have the same kinds of models, like the Bayesian models in particular, that are implemented in FSL. So I do think that like a lot of the stuff in SPM and FSL, there is no equivalent right now, but nothing prevents you, having said that, from doing all the pre-processing, or much of it at least, or just like any sort of preliminary operations or operations on the statistical maps in NumPy and Pandas. So that I would certainly recommend. And you can still use FSL for the actual estimation step in the middle. Yeah, sorry, I thought that's, so yeah, if you're starting issues getting those notebooks to show up, you do need to stop the server. Yeah, logging out alone won't help. Okay. So I guess I'll show you one other thing. I mean, there's any number of things that are kind of neat and we could talk about, but so I mentioned the group by. Well, actually, yeah. Actually, yeah, forget the group by. So one of the things that you'll often want to do is you'll want to apply like the same operation to each column or each row. You'll just want to essentially loop over a row or a column, and you could write. Pandas data frames are also iterable structures. You could write for loops again. So you could say for I row in data rows, for example, and that will give you the index in the row and can construct a for loop, but that's a lot of typing. Let's say you have some custom function you wrote. So my clever function, it takes Pandas series, which is just like one column as opposed to a data frame. And let's say it's extremely clever, it just adds 1 to it. I mean, like the only point here is to show you the kind of the application, not the actual function, which can be anything. Right, so this is a completely useless function. You could do this just by adding 1. You could literally just type data plus 1, and that would do the same thing. But if it's a more complicated function, and it's not built into the Python language or to Pandas, what you can do is you can use apply. So apply is basically says, actually kind of like apply in R, right? So you apply along a particular axis some function. So here I say take this data frame and apply my clever func, which could do anything, like completely arbitrary. And okay, this will fail because some of the columns are strings. And so let's take, let me just grab, I don't know. I'm pretty sure these are all numbers at this point. Okay, so I'm just pulling out some numerical columns and applying this function I just wrote. And so this is much faster than writing a for loop, especially if you already have in your environment this function you want to apply. There are also these things called lambdas, which are part of the Python language. For those of you who are familiar with like JavaScript, this is basically the equivalent of an anonymous function or closure. It's like a little piece of code. It's essentially a function, but it will go away as soon as this executes. So you don't even need to define this if it's a really short thing. For instance, I often use a really common little lambda I use this to standardize the data. So you could say x minus x dot mean divided by the standard deviation. Oops. No. Oh, I'm sorry. There's no return statement in lambda. So a lambda is just, this is an equivalent way of writing what I just did. This is a little Python trick, actually, not Pandas. A lambda function basically, this is kind of like the equivalent of writing def. Right? So here, every column now is being passed in as the x temporarily. This line gets executed and the result is returned. And so you can, this is a way of, for example, standardizing all the columns very quickly without having to define a new like standardized operation or something. It might be a little confusing, and I'm just trying to illustrate that there's lots of power in this package, and it's just a matter of kind of learning to work with it. Last question I'll take, and then we'll stop. Is it possible to rearrange the order of columns and or rows in data frame pandas? Absolutely. In fact, this is actually true of Numpy too. You would just pass the new indexes you want. And so, for example, let's really quickly construct a new data frame. Column is called Apple. Those are the values. And then we have maybe banana, and that has different values. So there's lots of ways to construct data frames. So just to show you, now we have a data frame. If I wanted to re-index those, I could just say, if I wanted to, let's say, switch the order of the columns, I could just say, let me practice what I preach, which is use the full-blown load indexer. I can even just pass the new order I want, right? So that will just reorder those. And the same thing with index. So there's lots of other ways you can do this kind of thing, but the general answer to any question you could probably ask is, yes, you can do it in Pandas. It might not be one line, right? So you might have to write like a few lines of Pandas code, but there's no reason why, as long as you're talking about like operations on tabular data, there's a very good chance that what you want to do can be done in a small amount of code. All right, so thanks for all the questions. These are great. I will stop there. Feel free to ask in the Slack channel as well. I haven't actually had a chance to look at it all, but I will now. And hopefully that'll at least get you started. And I very much recommend working through Jake Binder classes, both Numpy and, in fact, the whole, if you have the time, I would just like work through that whole book. It's really stellar. So I'll stop there, and I guess we have a lunch break. For some of you, it's probably dinner. And then we'll resume with a couple more talks afterwards. All right, so thanks.